and
Yeah.
now I'm not.
Welcome everybody to our fourth live session, actually our third since we skipped a couple weeks ago. We got a bunch of great questions this year. Sorry about that. We got a bunch of great questions this week, and we're going to start off with what does object-oriented programming mean? And I think Phil should take this one.
All right, I'll try this one. So object-oriented programming is what we call a programming paradigm. It's primarily a perspective on problem solving with programming. Another example would be procedural programming. So procedural programming, we break a problem down into the things that the program needs to do to solve the problem, and for each of those things we write a procedure or a function. In object-oriented programming, we take a higher level, more abstract approach to problem solving, and we look at the problem in terms of what the problem and its solution is composed of. So if we're dealing with a problem of, say, managing inventory at a pet store, then we're looking at the objects involved, like the inventory items, maybe various pets, maybe various pet foods, maybe various pet toys. And for each of those items, how many do we have in stock? And if we need to reorder them, where do we reorder them from? So there's going to be suppliers for these items. And we have customers. And then as we identify the objects that compose the problem space, we attempt to design a solution in those same terms. So we try to create a computational representation of each of those kinds of objects, a computational representation of an inventory item, a computational representation of a supplier, a computational representation of a customer, and we pack into those objects responsibilities that are associated with those objects, so that an inventory item might need to know its price and how many of those are currently in stock and who we would reorder from. And a supplier might need to know the contact information from that supplier and the list of products that that supplier supplies to us. And so we decompose the problem not into a very large number of functions or methods, but a smaller number of objects, each of which has some functions or methods and some variables to store some information. And then we compose a solution in which objects of these different types collaborate in order to solve the problem.
Yeah. So this is object-oriented programming is sort of a design practice more than it is a sort of programming principle. We're going to introduce it very briefly at the end of this class to just sort of get you used to some of the concepts and stuff like that. But something like object-oriented programming as a whole, being a master of it takes a long time to develop. It's a experiential sort of skill, and it takes time to develop that. So you will learn some principles of programming in this class that everything we're learning can be applied in object-oriented programming. And object-oriented programming is more about how you architect a program to solve a problem.
Yeah, and then different programming languages that support object-oriented programming may do that in different ways.
Yeah.
A very common approach is class-based object-oriented programming, which is what we're going to study when we get to Java in the second half of the semester. But there are other ways to do object-oriented programming as well. So it's not tied to a specific programming language, and it's not. It doesn't allow you to do anything fundamentally that you couldn't do in any other programming paradigm. It's just an other useful way to solve problems.
Yeah, totally. So our next question is, how do we use the Python platform to do product style programming, like using for like developing games or making calculators or standalone type programs? So Python is a what's called an interpreted language. There is the script that you write in Python. All of that gets shipped off to an interpreter, which is a special program that takes that script and executes each of the instructions one at a time, just like we've been experiencing. But that runs on top of something else. That runs on top of the operating system. That runs on top of your computer. And you can't basically execute a Python script without the Python interpreter. So it's not commonly used for finished product type programs that you would normally see. Python is what they call like a systems language, where it's running in sort of a bigger system and it's taking data from a bunch of other things, and it runs behind the scenes. So there's lots of products that you use, things like Dropbox and Google and all of this stuff that have Python. They're using Python to run the engines behind these things in the background, but you don't download a program that's written in Python. Later on in the class, we'll be working on the Java programming language, which is much more portable, and it typically runs with on most machines that have the Java environment installed. So it kind of works in a similar way. We'll get into the details of that later, but Java is much more commonly used to produce program products, and apps and things like that. So you'll be able to see how to do that. I do recommend practicing in Python. If you want to write games, there's a great framework called Pygame that allows you to build programs in Python, build games in Python, platformer style and 3D style and all kinds of stuff like that. And that can be really fun. That's a really great way to learn how to do more Python type stuff. And all of everything you will learn in Python doing that kind of stuff is very transferable to lots of other languages.
There's also a really great book out there that I think aligns really well with the primary purpose and best practices of Python, which is called Automate the Boring Stuff.
Yeah. So the idea there is to have Python tie into all of the stuff that you normally might do as part of a normal business activities, like emailing a bunch of people or working with spreadsheets or working with Word documents and all kinds of stuff like that. And you can write a script that does all of the dumb repetitive tasks that are really, really a pain and suck up your time. And often in less time, you can write the script in a short amount of time. And every time you run the script, it saves you hours and hours of manual labor that you would have normally had to do just copying and pasting between two programs, which is super annoying. So that's a really great thing to check out. I kind of answered that one. Let's get into some questions about the midterm exam. So the first one is, how many sections will there be? What's the weighting between theory and practical problems? And how long it takes to complete the exam? So there's two main sections in the final exam, or in the midterm and the final exam. They're both structured similarly. There are the multiple choice theory questions, as this user pointed out, and there are the practical programming problems. They're split 50-50 between the two weights, so half and half is worth each. And there's about
60 theoretical questions.
Yeah, there's 60 theoretical questions, and I think 8
or 10
applied. 8 or 10 applied questions. And the applied questions are given in Vocarium. They are little tiny programming challenges. So write a line of code, write a function, write a decision statement, that sort of stuff. So they're very simple. They're not as big as they're not anywhere near as complicated as our
project challenges.
Yeah, our project challenges. But they are going to test your knowledge, and you should be prepared to do that. The multiple choice questions are things based on the vocabulary, the theory, and being able to identify parts of programs, being able to predict the output of given programs. Basically, if you look back through the course and look back at your skills challenges and look back at the knowledge checks, you'll see a lot of the same kinds of questions that you'll encounter on the midterm exam. And make sure that you check out the midterm study guide for a more focused list of specific topics that we're going to be looking for and testing for in the midterm exam itself.
Cool.
Notes. So you can have one page of notes written or printed. You can, it's limited to one 8.5 by 11. That's an A4 sheet of paper. And it's handwritten or printed is allowed on both sides. So you can put basically whatever you want on it, including lists of Python functions and all that kind of stuff. at any font. If you've got a magnifying glass and you want to make it super tiny, go for it. There's no restrictions there. But we want you to try and internalize some knowledge, and actually creating this this note sheet will help you study for the exam itself. So just try to keep that in mind as you're developing your note sheet. It's not something that is really a reference. It's something that will help you find and organize your own thoughts.
Right. Additionally, you can bring 2 blank sheets of A4 8.5 by 11 for scratch paper if you need that. So it comes in handy sometimes to sketch out your ideas. And if you're trying to predict what a program will output, it's nice to kind of keep track of the values of the variables, and some scratch paper comes in handy for that. Handheld calculators or the calculator app on your computer are okay.
Yep.
But web-based calculators and use of your cell phone is not okay.
Yes, yes. And remember that you need to have a webcam available so that our secure testing service can see what you're doing. If you're going for either if you're ID verified and attempting this for credit, then you need to make sure that you're prepared for the proctoring service. Okay. So we're getting towards the end of our questions. We've got 2 more that we're going to answer from Bill that we just got online. But if you guys have any questions for the rest of this session, go ahead and post them into the chat on here, and we'll answer them right after we finish these next 2 questions.
All right, some good questions here. It seems there are multiple ways to create most algorithms. When writing code, are there types of decision making that tend to make more or less more or less processing power? Yes, the answer to this is yes, and this touches the very core of computer science, right? So a big element of the theoretical aspect of computer science is fundamentally what's computable and what's not computable.
Yeah.
And then on top of that, how easy is it to compute some given thing, or are there algorithms that make things that appear to be very difficult very easy?
Yeah, for a computer to do. So this is the central challenge of computer science. Phil mentioned computable or not computable, and basically this is the theory around what kinds of questions can we use computers to answer. Can we find the solutions to certain kinds of questions, or is it impossible to literally answer them without having infinite time and memory on our computing machines? And that's a whole area of research. Once we find out that something is computable, it's about how do we do it efficiently, right? So how do we if we have limited memory, how do we spend more? How do we minimize the amount of time that it takes to solve, find the answer to certain kinds of problems? And simple problems can be things like, how do I sort a list of names most efficiently, right? There's literally hundreds of different kinds of algorithms that help us solve that very simple problem, and we analyze their behavior in how long it takes us to do that, or how many steps it takes for the computer to solve that particular problem for a given list length, and stuff like that.
On the other extreme, you've got very complex problems like what would be the optimum combination of medications and treatments for a particular patient's cancer.
Right.
And that's an incredibly complex problem that we haven't yet found efficient solutions in computing for problems like that.
Yeah.
Doesn't mean they don't exist.
Right.
We haven't proven that they don't exist yet.
Right.
The question also breaks down into 2 components, in my opinion. There's the aspect of the processing, so what the computer's CPU has to do in order to tear apart the data that it's given and create an answer. And then there's the use of memory resources. So on one side, you have the algorithms, and on the other side, you have what we call the data structures. And so for a given problem, when we're trying to create an efficient solution, it's a combination of choosing and developing the best algorithms and the best data structures to represent the data that's part of that problem. So.
Yeah. And those choices very drastically affect each other. You can, by organizing your data in a certain way, you open up the ability to use a whole different classes of algorithms. And all of this stuff is something that if you want to continue learning to program, you should look up those two words as the next classes that you should probably take: data structures and algorithms. Usually they're together because they're very much married and very related to each other. So figuring out or finding a class that teaches data structures and algorithms allows you to apply the programming principles, the basics that you're learning in this class, at the next level, and figure out how to solve more complex problems that deal with lots and lots of different kinds of data very efficiently. Cool.
All right, this next question is, are there norms or templates amongst programming, and when to use what type of decision structure so that programmers are more easily able to fix problems with code they didn't individually write? So I feel like there's maybe a couple of different questions buried in here. This last part about being able to easily fix problems with code that you didn't write. So and this is a common thing, that if you become a software developer, a programmer, you're going to find yourself in a situation where you've inherited a code base that needs to be maintained and evolved. And there may be hundreds of thousands or more lines of code there for you to work with, and you're going to have to somehow wrap your head around that. And what you'll find is there are a lot of practices that the programmers that wrote that code could have done or hopefully did do that make that process much easier, or hopefully didn't do but might have done that make that process much more difficult. So some of those things are things like choosing descriptive yet concise names for your variables and your functions. That helps a lot. And some of the other things are like keeping your functions small and flat, so that you don't have deeply nested decision logic and looping structures inside of there. And each function performs ideally a single well-defined task. So that if something's going wrong in your program, you find the function that's responsible for that, and you know that the problem is somewhere in that few lines of code. So there's a lot of things like that you can do. On top of that, you can use good commenting and some formatting styles with indentation and white space. That all helps. But I think there's a deeper question here that's talking about things like decision logic structures, which to use and when to use them. And this starts to approach a discussion about patterns. It's a common topic in other engineering endeavors. If we're building skyscrapers or suspension bridges, there are design patterns of best practices that have been tried and proven to work that we can rely on. And software engineering and programming is new enough that we have a small set of patterns in different domains, some object-oriented patterns, some patterns with regard to decision logic and iteration logic. But we really haven't laid down our fundamental structural patterns and guidelines in this discipline, in my opinion, yet, which I think makes the field exciting and interesting. So you can contribute to that. So the nascent beginnings of that are there, but a lot of that work remains to be done.
Yeah. And to put it in context, like mechanical engineering and civil engineering and all of these disciplines have literally been around for hundreds of years. And computing programming as an industry is barely 50 years old, right? So we're still pushing and discovering kind of what we want this world of programming to look like. And we see that with the invention of new programming languages all the time. Like Rust is very popular. That's only been developed in a couple of years. Python was developed less than 20 years ago, and it's only now becoming very popular. And we're trying out new ways to express ourselves at the most fundamental level, much less these large structures that are sort of the big patterns for solving problems. But if you look up stuff like for higher level design challenges beyond data structures and algorithms, there's another level which is actually called design patterns, where they've started to identify some of these big patterns for how we solve certain kinds of problems in certain kinds of applications and things like that. And you can read about that. You can take software engineering classes that help with that. And there's a lot of practice. You can go as far with this as you want, into exploring all the different ways that people solve different kinds of problems. And it's just putting newer, better, more advanced tools in your personal toolbox, which makes you an incredibly powerful programmer ultimately. Yeah. So we didn't get any more questions in the chat room. So that's all we've got for this week. We know it's super intense. We see a lot of you guys having comments and questions about the automatic stock trader and the other 2 project challenges that we have due this week. Keep it up. There's lots of great answers there. And we're all there watching and helping, trying to help you guys out as you go. Keep asking questions and we'll keep answering them. Keep your sort of nose to the grindstone and we'll power through this together.
Yep. This is, I think, the most challenging section of the course.
Absolutely.
You know, from just prior to the midterm to just after the midterm. And from there, it should start to ramp down a little bit. Not that there won't be challenge. There should be plenty of challenge, but it should feel a little more of a downslope than an upslope.
Yeah.
So stick with it.
This week, or these 2 weeks and next week with the midterm and starting Java, this is the most intense part of the course. So if you're feeling the pressure, if you're feeling the stress, you are absolutely not alone. This is done by necessity. We wanted to really hammer home all of the messages that we've been building up to for the rest of the semester. And we wanted to make sure that you have a lot of practice and you're demonstrating that. So if you power through here and if you're feeling pressure, that is totally normal. It's expected. Everybody is struggling with you, and we can all help each other out, and we'll all succeed if you stick with it.
Cool.
Awesome. See you guys in a couple weeks.
See you.